Welcome to all of you. Today's design problem is based on that slab which is supported by brick wall. It will be called as or designed as a two-way simply supported type of slab. So let us go through the design provisions and what are the codal guidelines which we have to follow while doing the design of a RCC type of two-way simply supported type of. Now first of all, let us go through the problem statement, that means the slab which we have to design, and as per the statement the slab is of a residential type of building having dimensions, that means longer span as well as shorter span are given. So dimensions of the slab is 4.5 meter by 6 meter, and this slab is to be designed as a simply supported type of slab which is supported on all of its four sides on 230 millimeter thick brick walls. Here we can assume that imposed load we can take it equal to 2 kilonewton per meter square, and the load due to finishes on the slab we can take it as 1 kilonewton per meter square. Design of floor slab we have to do. This is a floor type of slab, and we can use M25 grade of concrete and Fe 450 steel, as well as we can assume that this slab is going to be located in the building, in a residential building, which will be subjected to or exposed to mild type of exposure conditions. So very first step is, as usual we do, that is the selection of grade of concrete and steel. Now in this particular problem, grade of concrete as well as grade of steel is already given. So whatever the data given, let us go through. First of all, the width of the masonry support is 230 millimeter at the walls, and slab is exposed to mild exposure conditions. Grade of concrete is already given in the statement, that is M25, as well as grade of steel is Fe 415. And since it is of mild exposure conditions and a residential type of building, so we can take clear cover for reinforcement for mild exposure condition, that can be taken as 15 millimeter, and accordingly effective cover we can assume is as 20 mm, and the reinforcement bars which we are going to use as a tensile reinforcement, they will be reinforcing bar of high strength type of steel and having diameter 10 mm. So adopting M25 grade of concrete and steel bar of high strength steel, that is Fe 415 grade. So ultimately, the design of the section will be according to provisions mentioned in IS 456 2000 version as simply supported type of slab, and the method which we are going to apply, that is limit state design method. In step number 2, where we are going to fix the dimensions of the section based on the grade of steel and based on grade of concrete. So as mentioned in the statement, that size of the slab is 4.5 meter by 6 meter, and which is supported on the 30 mm wall. So here let us consider that a shorter span is along x direction and a longer span is on y direction, along y direction. So Lx we can take equal to 4.5 meter, and Ly, that is longer span, is 6 meter. So taking the ratio of the both the span Ly by Lx, which we got, that is equal to 1.33. So this is less than 2. That means the slab which we are going to design, it will be a two-way slab. Now as per clause number 24.1, we can take Lx by capital D ratio, that means overall depth of the slab, that is equal to this condition. If you refer clause number 24.1, then in case of simply supported type of slab, this ratio can be taken as 30, and however, because you are using not mild steel, as well as you are using here high strength steel, that is Fe 415. So then as per the clause 24.1, this 30 ratio Lx by D, which is 30, can be multiplied by 0.8. So ultimately here we are getting Lx by D is equal to 24. So based on this ratio, we can just work out what should be the overall depth. So overall depth we can take 4500 by 24, that is 187.5 millimeter. So we can provide approximately 170 mm. Since based on the experience we can judge this depth required is coming out to be higher. So we can try by taking it is equal to 170, which is round off figure, and over effective depth along the x direction, that will be 170 minus 15 is the clear cover, and 5 is the half of the reinforcing bar, which is parallel to the shorter axis or shorter span. So we get dx equal to 150 mm. Similarly, we can obtain the effective depth of the slab required along the major axis, or better to say that longer span. So since that reinforcement is placed above the reinforcement along the shorter span, so we will be able to get, after calculation, the effective depth which we are able to provide here along y direction or along some longer span, that comes out to be 140. So it is very much clear here that we have provided overall depth as 170, and effective depth along shorter direction is 150 mm, and effective depth along longer span comes out to be 140 mm. So since we have adopted 10 mm dia bar as reinforcement, so from these two values we can work out what is the average effective depth. So average effective depth is the mean of these two values, 150 by plus 140 by 2. So it comes out to be 145 millimeter. Now after that we can go through the step number 3. That means here we will be doing the calculation regarding effective span length. So very first point is effective span length can be calculated as, you see the clear span between the two supports along the shorter direction, and this 150 we have taken as effective depth of the slab. So it comes out to be 4.650, and center to center support will come out to be 4.75, and we can take the least out of these two values. So ultimately Lx, that is effective span along shorter direction, that will be equal to 4.65 meter, and similarly along longer span it comes out to be 6.14. Again we have to use same methodology to work out length of the span, that is effective span along longer span length. So here we have to apply the check whether Ly by Lx is less than 2. Yes, it is coming out to be less than 2. So we can proceed with the design of this slab as a two-way slab. Now step number 4, here we are going to do the calculation regarding what are the various loads coming on the slab. So we have taken it into two parts. Step number 4a, where we will be going to discuss the loading calculation. So first point is we have to work out the self weight of the slab per meter width, and that comes out to be W net load is equal to, this is 1 meter, and 0.17 is the overall depth of the slab, and 25 is the unit weight of the RCC. So after doing the calculation, we get this will be equal to 4.25 kilonewton per meter square. And second point is the dead load due to the finishes, whether it is given in the statement or we have to assume. So here, since it is information is available in the statement itself, so it comes out to be the dead load again due to finishes, it comes out to be 1 kilonewton per meter square. And third point is live load on the slab per meter width. So again, live load is also given in the statement, 2 kilonewton per meter square. So we can take that value, W live is equal to 2 kilonewton per meter square. So ultimately we can add up these three values. So these are the maximum possible loads which the slab is able to take in the future. So that's why total load, that is in the form of UDL, WD, it comes out to be, after addition of these three values, it comes out to be 7.25 kilonewton per meter square. and then using partial safety factor for the loads, we can work out total design factor load. That is ultimate factor load is comes out to be 10.875 kilometer per meter square. Now here you can see this diagram. In this diagram, this is the longer span of the slab and Lx is the shorter span of the slab. That means this will be 4.5 and this will be 6 meter. So here what we have to do, since it is simply about a type of two-way slab, so we have to take the two strips into consideration while designing. One will be parallel to shorter span and other will be parallel to longer span, having equal width, that is 1 meter of each strip. So in step number 4b, we can calculate the bending moment, and for a simply supported type of slab, here we are going to take the strip of the slab and the maximum bending moment is taken at mid of the span of the simply supported type of slab. And for the calculation of bending moment, we have to take bending moment coefficients from table number 27, and this table number 27 is available in clause G2.1, that means annexure G, and the clause number 2.1 of IS 456. So for first of all, we have to calculate Ly by Lx ratio, which comes out to be 1.32, and then bending moment coefficients based on this value, we can get alpha x and alpha y from table number 27. Now alpha x and alpha y, which we have obtained from table number 27 based on this span length ratio and along x direction as well as y direction. So keep in mind here when we are saying x direction, that means it is parallel to the shorter span, and alpha y is the bending moment coefficient along the longer span. So after doing the interpolation from the values given in table 27, we are able to get alpha x is equal to 0.094 and alpha y comes out to be 0.0542. Now bending moment calculation we can do along the both the spans, longer span as well as shorter span. So when we talk about the shorter span, then mx is given by this formula, and where alpha x is equal to 0.094, W we have taken, that is the ultimate factored load 10.875, and Lx is 4.65, that is effective span length along a shorter span. So ultimately we are able to get this value 22.103 kN, which is the maximum bending moment along a shorter span. Here we have to do the correction. That means this is the bending moment along longer span. So here we can do one correction. This is longer span. So longer span, that is bending moment along longer span is my, which is given by alpha y w into lx square, and putting the value of alpha y w and lx square, we are able to get this value. So you can see here that along longer span, bending moment is lesser than bending moment which is along the shorter span. So that's why we are taking always shorter span as a more prone to the bending, or we can say the shorter span is more critical as compared to the longer span. Now in step number 5, what we will be going through, we are going to discuss how to apply the check for depth required, which will be able to take care of the bending moment. So again, we are assuming that the section which we are going to design will be a balanced type of section, and we can use this formula for the ultimate bending moment, that is 0.138 FCK BD square. Here, since we are going to design a strip along each direction, that is along shorter span as well as along longer span, and taking width is equal to 1000 millimeter. So first of all, let us calculate what is the effective depth required. So D required will be taken by this formula, putting all the values. So we have taken the highest value of the bending moment, that is 22.03, and into 10 raised to power 6, and FCK is 25, and width we have taken 1000 millimeter. So ultimately depth required comes out to be 80.04 millimeter. But the depth which we have provided, that is 150 millimeter, which is quite higher than depth required. So here we can say that check for depth is okay and depth is sufficient. So we can say depth provided is sufficient to register the bending moment. Now we can apply the check for XUYD ratio. And by putting all the information available, we are able to get the value of XUYD, that is equal to 0.115. And based on this value, we are able to get what is the depth of the neutral axis along when we are considering shorter span. So XU comes out to be 17.25. And since from table which is available in ISA 456, we can find out what is the XU max by D for Fe 415 type of steel. So that value is 0.48. So it is very much clear that whatever the effect XU by D ratio comes out to from the section which we have provided, that is quite lesser than the limited value. So we can say the section provided is under reinforced. So this check for the depth required is sufficient, and we can say it is. Now let us work out in step number 6 what is the reinforcement requirement. So in this step we are going to discuss, we are going to calculate the reinforcement. So first point is required area of steel along the shorter span. So we have termed it as AST1, and which we can calculate from this equation, which is applicable for a balanced type of section. So ultimately this will be give you the value, and so we are obtaining that is the area of steel required parallel to shorter span, that is 428 millimeter square. Now that means in reinforcement required is 428, which we have to provide in 1 meter width of the slab based on the center to center spacing, as it is similar to the design problem which we have discussed in case of a 1 meter slab also. So what is the spacing required so that we are able to provide 428 millimeter square of area of steel? So by using this formula which we have discussed in detail in the previous lectures, so spacing required, center to center spacing required between two bars comes out to be 183.5 millimeter. And when you refer the clause 26.33 part B, which is giving the guideline and restricting what should be the maximum spacing limit, so it is comes out to be 300 millimeter center to center. So that means we can provide 10 mm dia high strength steel bar at the center to center spacing of 180 millimeter, which is parallel to the shorter span. And when we provide 180 millimeter center to center spacing, and after doing the reverse calculation, we are able to get that how much is the area of steel which we have provided. So that comes out to be 436 millimeter square. So this will be the way how we have to provide the steel in the shorter span. That means it is parallel to the shorter span. So another thing which we have to keep in mind that first of all we will be providing steel parallel to the shorter span. Then when you work out the steel required longer span, that will be provided above the steel which we have provided here in the red bars, that is along the shorter span. Now again in continuation to step number 6, that is 6b part, here we are going to calculate what is the steel required which we have to provide parallel to the longer span, that it is AST2. So AST2 similarly we can get this value from MUY value which we have already calculated. And after doing the calculation, we are able to get that the area of steel required parallel to longer span comes out to be 266 millimeters square. And that means this much area is to be required, and which have to be provided in 1 meter width of the slab based on center to center spacing. So again, similar to previous step, we are able to get that the required spacing between parallel bars parallel to steel that we are providing parallel to longer span. That comes out to be 295.6 millimeters center to center. And again, going through the Kotal guideline, what is the maximum spacing required is, or limiting spacing, that is 300 millimeters center to center. So ultimately what we are going to provide here, we are providing 10 mm dia bar at a center to center spacing of 280 millimeter, which is lesser than 295, so it's okay. And based on this value, we are able to provide the area of steel, that is 280 millimeter square. And this 280 millimeter square is greater than the area of steel required. So again, this step is also okay. And these are the green bars which we have provided, and these were provided above the steel which we have provided parallel to the shorter span. Now in step number 7, we have to apply the check for shear, and we can refer clause number 40. So similar to the previous type of one-way slab, again, the critical section for shear is at a distance b from the support. Here, effective depth we will take, that is the average depth which we have already calculated in the previous steps. So you can just see this diagram here. This is the slab, and this slab is supported on the simple type of supports, that means walls, and 10.875 kilonewton per meter is the total load in the form of UDL, which is on the slab, and the shorter span, that clear span, is 4.5 meter. So based on this data which is available, we have to work out, we have to calculate what is the shear force at this section, which is at critical section, at a distance that is equal to effective depth from the face of the support. So ultimately we are able to get this value, that is 21.65 kilonewton. So factored shear force at critical section comes out to be 21.65 kilonewton. And then the nominal shear stress we can work out tau b, and here you can see that we have used depth is equal to 145, width is already 1 meter, and this shear force is 21.65, 10 raised to power 3. Here we have to raise into power 3. So ultimately it comes out to be 0.149. Now what should be the design shear strength of the section as per code? That will be tau c. So for that we have to refer table number. And for table number 19, when we have to refer, we need percentage of steel. So percentage of steel worked out to be 0.29. And then referring table number 19 and doing the interpolation between the values available, tau c comes out to be 0.3808. Now you can see this tau c is quite higher than tau b. That means the section is sufficient in taking care of the shear forces, which, or you can say shear stress. So this is the shear stress capacity of the section, and this is the maximum shear stress coming on the section. So tau c is greater than tau b, so we can say the section is safe in shear, and no shear reinforcement is required. However, we will be providing later on bent up bars also. Now in step number 8, we are referring clause number 23.2.1, and we will be applying check for a deflection. So check for deflection is to be applied, we have to refer this clause. Now check is to apply it along shorter span, since it is more critical. Why it is more critical? That we have discussed in the previous section. And here we have to work out what is the Lx by d maximum value, and that should be lesser than 20 into kt. Now what is kt? As we have discussed in one way slab also, this is the reduction factor we can say, and that we can obtain from figure number 4 of IS 456. Now what is Lx by d? That is actual, and it is 4500 by 150, so it comes out to be 30. And for calculation of KT, and to refer figure number 4, first of all we have to work out what is FST, and this will be the again same formula which we have used in one way slab. And after putting the information which we have obtained in the previous steps, we are able to get FST is equal to 236 MPa, And the percentage of steel which we have provided is 0.29 FST 236. So referring the figure 4 from IS 456, we are able to get the value of KT is equal to 1.60 approximate. And so 20 into K2 comes out to be 32. And Lx by D which we have provided should be lesser than L by D limited. So whichever we have provided, that is 30 and the limiting value is 32. So we can say this slab section which we are designing is safe in deflection check also. Let us discuss and apply the check for development length required. So again we have to refer clause number 26.2.1. Here you can see the diagram which we have already discussed. So we have to calculate first of all what is the development length required. And putting all the information, we are getting LD is equal to 403 millimeter. And as per clause part A of 26.2.3.3, first of all we have to calculate what is the embedment length of bar, which we can take up to the support or within the support embedment length, and that embedment length should be greater than LD by 3. So embedment length we can calculate, which is you can subtract clear cover which is required, and a clear cover that we can subtract from width of the support, and it comes out to be 205. For more detail you can if you have any doubt you can refer same guideline which we have discussed in design problem of one-way slab, and LD by 3 comes out to be 134.3. So it is very much clear that embedment length is greater than LD by 3, which is the condition given by IS 456. Now part C of clause gives you the value, that is in case of simple support L by D should be less than this formula, and after putting all the values, since we are taking bent up bar, again we take M1 value 50% of the ultimate bending moment, which is 11.05, and shear force which we have calculated already, that is 21.65. And L naught is the anchorage length of bend, since we are here also providing the bend. And again we have to refer this clause 26.2.1. The anchorage value we obtain is comes out to be 8 times dia. So here diameter of the bar we are taking 10 mm, so it comes out to be 80 mm. So ultimately we got this right side of the equation 744, and LD was required was 403. So ultimately this equation is also justified here. So we can say the check for development length is also okay here. Now in step number 10, we are going to discuss reinforcement detailing. That is the reinforcement detail for two-way simply supported type of RCC slab. So you can see here one by one. First of all, we will be focusing on the plan. So this is the plan of the slab. So this plan, you can see the width of the support, that is brick wall, is 230 mm on all sides. So since the slab is supported on all sides by brick wall, and the clear span along the longer side is 6 meter, as we have discussed, and the clear span along shorter direction is 4500 millimeters. So all dimensions are in millimeter. Now black color bar indicate the alternate bars are bent up bars, and we are providing the bent up bars as per the code of provision. And here you can see that these are 10 mm dia bar at a center to center spacing of 180 millimeter. First of all, we will be providing this black color bar, that is the steel parallel to the shorter span, and then this red color bar gives you the information regarding these are the steel bar, that is 10 mm dia and 280 mm center to center. So here whichever the steel bar we are providing parallel to longer span, they are having more spacing, so that means we will be providing lesser steel parallel to the longer span and a greater value of steel parallel to the shorter span, since shorter span is more critical. So that's why we have to provide higher reinforcement parallel that direction. And here you can see that steel which we have provided parallel to the shorter span. So bent up, they are bent up in the upward direction at a distance 450 millimeter from the face of the support. And the steel which we have provided parallel to longer span, that is lifted or bent up at a distance 600 millimeter from face of the support along that direction. So when we can now here we have taken two sections, section AA and section BB. So first of all, this will be the section AA. Here you can see these black color bars. Since it is the critical side, black color bars are at a lower end, and above that we are providing blue color type of bars. And you can see the black color alternate bars are bent up in the upward direction. And effective depth of the section along shorter span is 150 millimeter. Overall depth is 170 millimeter. And the distance of a bent up of bar is 450. So here it is 450. Now, when we talk about the section, if we take section BB, which is parallel to the longer span, then you can see that these black color bars, which we have provided parallel to the shorter span, now they will be looking, you can able to see the cross section only, that is the dotted lines, and these red color, which are the bars which are parallel to the longer span. So they are above, they are placed just above the black color bars. So here we have differentiated bars as by color so that you can understand it more effectively. And now you can see the red color bars we have bent up at a distance 600 millimeter from face of support, as well as the effective depth along the y direction which we have discussed. Along longer span it is 140 millimeter, overall depth is 170. Here it was 150 and now it is 140, which is distance from the top of the slab, that means topmost fiber, up to the center of the red color bars. So these are the detailed drawing which we have to show and which we have to draw for designing, after designing the two-way simply supported type of slab. Thank you.